This problem and all other Calc 1 problems here at Rutgers can be found at Sarai Studies. Link is in the description box below. In this video, we're going to be doing some examples on how to find average, estimated instantaneous velocity, and exact instantaneous velocity. And recall, in the last video, I proved to you 4 points, and here they are. In the x-axis, we would have time, and in the y-axis, we would have the position at every point in time. And so in this case, t is equal to time, and x is equal to position. So let's say that this graph represents the journey all the way to your friend's house over here. This is your car at this specific point in time. We're going to call it t1. And then this is your car at this specific point in time. We're going to call this t2. So if I ask you to find the average velocity of the car between these two times, how would you do it? Well, anytime you hear velocity, think of slope. All you're doing is finding the slope between these 2 points. And what if I told you that this is the function that represents the position of the car at any point in time in its journey? Then I ask you to find the average velocity of the car between 2 to 4 seconds. Velocity is just slope. As soon as you hear the word slope, you should think, I need 2 points in order to find the slope. And so they're giving you the x values, they're giving you 2, and they're giving you 4. You would just need to find the y values, right? The position at those points in time. So we're given the function, so we can just say, okay, the position at time 2 is equal, this is 16 times 4, that's 64. Now we find the position at time 4, that is 256. So let's go ahead and update our graph. So time 1 is going to be 2 seconds, and time 2 is going to be 4 seconds. At 2 seconds is 64. At 4 seconds, our position is 256. Now we have our 2 points. So what's our slope formula? It's always going to be the difference between the y's and the difference between the x values. In this case, it's the difference between the position versus the difference between the times. And so average velocity equal to 256 minus is the change in position over the change in time. So then 4 minus 2. Here that is 192. 4 minus 2 is 2. That gives you 96. The units of average velocity is always going to be meters per second. So really we're saying that the average velocity of the car between 2 to 4 seconds is 96 meters per second. Just to be specific, this is your velocity formula. It's simply just the difference between your position over the difference between your time. What if I asked you to find the instantaneous velocity of the car at exactly 2 seconds? So as soon as you hear the word velocity, think of slope. As soon as you think of slope, think of that fact that you need 2 points in order to find the slope. So you need 2 points and you need to figure out what those 2 points are. That's a fact. Always 2 points for both average velocity and instantaneous velocity. Really what they're asking you is just to find the slope of this right here. We know that we need 2 points in order to find the slope. So how do we do this? Again, this is where point 3 comes in. The only difference between finding average velocity and instantaneous velocity is that for instantaneous velocity, you simply just have to pick a point that is really close to the instant you want to find the velocity at. In this case, the instant in time we want to find the velocity at is 2 seconds. So we simply just need to pick time that's really close to those 2 seconds. So maybe 2.01. That's just a little bit more. The point we're actually trying to find the slope at. So far, we have a point over here that's 2.01, which is just a little bit more than 2. And over here, we have 2,64. We have to go ahead and find the position at 2.01 seconds. If you plug 2.01 into the function, you're going to get 64.6416. And now you have your 2 points. You're going to use the exact same formula because, again, point number 2, average velocity and instantaneous velocity use the exact same formula. xy, 1, 2, 2. I know that my formula is y2 minus y1 over x2 minus x1. So the difference between my y, so 64.6416, is my y1 is 64. 2.01 minus 2. So 64 is positive. Here 64 is negative. You're simply left with a positive 0.6416. I have a positive 2 over here and we have a negative 2 over here. These cancel out and you're simply left with a 0.01 that is positive. The average velocity is equal to 64.16. But notice we don't refer to this as average velocity. Instead, we refer to this as instantaneous velocity. The idea is that because we picked a point that's so close to the original, difference was so small that we technically found the slope at that instant in time, 2 seconds. So in this case, at exactly seconds, we estimate velocity that instant in time be 64.16 meters per second. And at the top, I probably should say that average velocity of the car between 2 and 4 seconds. The journey is 96 meters per second. Right? And that's the difference between average velocity and instantaneous velocity. Velocity, they're always going to give you 2 points. You just simply plug that into the formula. Instantaneous velocity, they're only going to give you 1 point, and you have to find the second point that's really close to the first one, so that when you plug it in to the formula, number one, you're satisfying the requirement that you need 2 points, the slope formula, so you're kind of getting away with that. At the same time, the point is so close to the original that it's on a technicality basically the same point. So you're finding the slope at one point in time, at an instant in time, which is why we call it instantaneous velocity. Now, to be precise, we actually estimated the instantaneous velocity because there is still some difference between those 2 points. To find the exact instantaneous velocity, the exact slope at one point, we can limit the difference between the 2 points to be basically 0. And the way that we do that is by limiting the difference between the 2 points. We're going to call that h to 0 of the instantaneous velocity. But I'm not talking about this. I'm talking about like the second way to view instantaneous velocity, which I covered in the last video. So another way to view instantaneous velocity is, let's go back to time 1, time 2. This point right here is time 1, and then whatever the position is at time 1. And then this point right here is time 2, and then whatever the position is at time 2. But another way to think about this, another way to define time 2 is time 1 plus a little bit more. This distance, this change in time, we call that h, that difference between the points, this distance over here, because that's what this purple point is. It is literally this time plus a little bit more, this time plus a little bit more. So another way to rewrite this point is that this is time 2, but time 2 can be defined as time 1 plus a little bit more, and then the position at time 1 plus a little bit more. And so if we were to rewrite that in slope formula, again, that would be the change in y over the change in x. So what I like to do is I like to label this x1, y1, x2, y2. So we have that the slope is equal to y2, which is this, minus y1, which is this, over x2, which is this, minus x1, which is this. And notice how the t's cancel out, and we're left with positive h. And this is another way to view instantaneous velocity. So if we take this definition of instantaneous velocity and we limit the difference between the 2 points, which is h, to be 0, then we can find the exact instantaneous velocity, the exact slope, the exact velocity at an instant in time at this black point. Because this part is literally saying, hey, we're going to take this green part, this difference between the 2 points, and we're just going to limit it to be 0. And so when we do that, if we take away h, then it just becomes t1. And so taking the limit of instantaneous velocity gives us the exact velocity, the exact slope at this point, because we're taking away h. With this, we estimated the instantaneous velocity at this point, the slope at this point, because there was still some difference. That difference was 0.01. H still existed. But with the exact velocity, we limit h to be 0. Recall that this is our function x of t. So what this is saying over here is take our function x of t, and wherever you see t, add a little bit more. Add h. So we're going to take our function x of t, and wherever we see t, we're going to add h, a little bit more. It's going to become 16t plus a little bit more squared. And then this is our function x of t, so let's plug that in. We also know that t is 2, and so if we do the math, this becomes 4 plus 2h plus 2h plus h squared. This becomes 16 times 4 plus 4h plus h squared minus 16 times 4, which is 64 all over h. You can distribute the 16. That becomes 64 times 64h plus 16h squared. And then these 64's cancel out. And then we can factor out an h from here. So this becomes h 64 plus 16h. And then these h's cancel out. And we're left with 64 plus 16h. And we're taking the limit as h approaches 0. So we plug in 0 for h, because that's what the limit means, plug in 0. That cancels out and we're left with 64. And so therefore, at exactly 2 seconds, the velocity at that instant in time is 64 meters per second. So it is exactly 64 meters per second. That's the difference between estimating instantaneous velocity versus finding the exact instantaneous velocity. Here we said that we estimate that the velocity is 64.16 meters per second. And 64.16 was pretty close to the actual velocity. But the reason this is more accurate is because of this limit here, where we limit the difference between the 2 points to be 0, so it's practically us finding the exact slope at that point. Here, there is still some difference, and so therefore it's an estimate of the slope at that point. So the difference is we could say exactly that it's 64, and here we estimate. And this is just, average velocity.